Black holes follow strict rules. There is a limit on how fast one can feed and a limit on how heavy it should ever get compared to its galaxy. In 2024, astronomers pointed a telescope built to study the first galaxies at one distant black hole instead, expecting routine data. What came back broke the math completely, and nobody could explain it at first. Supermassive black holes sit at the center of nearly every big galaxy, including our own. The one at the middle of the Milky Way weighs about 4 million times more than the Sun. That is already hard to picture, but it is nothing compared to what astronomers started finding once they pointed powerful telescopes at the early universe. The trouble is timing. Black holes grow by pulling in gas and dust, and that process takes time. Basic physics gives a hard ceiling on how fast this feeding can happen, called the Eddington limit, named after the astronomer who worked out the math a century ago. Past that ceiling, the radiation pouring out of the black hole should push incoming matter away, choking off its own food supply. Given that ceiling, a black hole should need hundreds of millions or even billions of years to reach supermassive size. Yet scientists kept finding supermassive black holes in galaxies less than 1 billion years old, when the universe barely had time to cool down after the Big Bang. Something was letting these objects grow far faster than the math said they should. For years, nobody had a telescope sharp enough or sensitive enough to catch one of these black holes in the act and figure out what was really going on. Two of astronomy's biggest workhorses, the Hubble Space Telescope and the Chandra X-ray Observatory, had been hunting for early black holes for years before this story really got going. Hubble is built mainly to see visible light, and Chandra is tuned to X-rays, both useful for spotting black holes that are actively feeding and glowing brightly. The problem is distance. Light from the early universe gets stretched out on its long journey to us, shifting from visible light into infrared. The earlier and farther away a galaxy is, the more that stretching happens, and the faster it slips outside what Hubble and Chandra can clearly detect. Ground-based telescopes ran into a similar wall. Even the best infrared instruments on Earth have to look through our own atmosphere, which blurs faint signals from deep space and buries the small details scientists actually needed. Researchers could tell that something odd was happening with early black holes, but they could not pin down the details well enough to explain it. What the field needed was an infrared telescope sitting far from Earth's atmosphere, sensitive enough to pick up the faint glow of gas falling into a black hole billions of light years away, and precise enough to separate that signal from all the noise around it. That combination did not exist yet. It was still being built, tested, and slowly prepared for a launch that would change what astronomers thought they knew about the early universe. The James Webb Space Telescope launched on Christmas Day in 2021, built to look back toward the very first galaxies that formed after the Big Bang. Studying nearby black holes eating too fast was not the headline goal, but the same infrared sensitivity that let Webb see ancient galaxies also made it perfect for spotting faint signals around distant feeding black holes. Webb carries an instrument called the Near Infrared Spectrograph, or NIR SPEC, which can split incoming light apart and read the fingerprint hidden inside it. That fingerprint tells scientists how fast gas is moving, how hot it is, and how much energy is pouring out of it. Details that are almost impossible to get any other way. Teams of astronomers built survey programs specifically to hunt for faint active black holes in the early universe using this instrument, sifting through thousands of faraway galaxies, hoping to catch a handful with something interesting going on at their center. If you're enjoying this breakdown, hit subscribe so you don't miss where this bracket goes next. One of those programs, a survey looking for actively feeding black holes billions of light years away, turned up a target that immediately stood out from the rest. Most early black holes detected by Webb are faint or completely invisible in X-rays. This one was not. And that single detail was the first hint that something unusual was happening. The object got a technical name, LID 568, and it sat about 1.5 billion years after the Big Bang, early enough that it should not have had time to grow very large at all. A team led by astronomer Hyewan Su at the International Gemini Observatory used Webb's NIR-SPEC instrument in a special mode that let them pinpoint the black hole's exact location, something earlier data had struggled to nail down because the object was so faint and so hard to place precisely. Once they had a clean measurement, the numbers coming back made almost no sense. LID 568 turned out to be relatively small by supermassive black hole standards, weighing around 7.2 million times the mass of the Sun, similar in scale to the black hole at the center of our own galaxy. But the light pouring out of the material swirling around it was far brighter than a black hole that size should ever be able to produce. When the team calculated just how much matter it was pulling in, the answer came out to more than 40 times the Eddington limit, the theoretical speed limit for feeding. Researcher Julia Scharwachter of the International Gemini Observatory described it simply, saying the black hole was having a feast. Webb's data also revealed powerful outflows of gas rushing away from the black hole, evidence that a huge portion of its growth may have happened during one short, extreme burst of feeding rather than slow, steady growth over millions of years. It offered a possible answer to why some early black holes seem to have grown up so fast, suggesting brief bursts of extreme feeding could pack in enormous amounts of mass in a short window. That explanation felt like a breakthrough. But the story of overfed black holes was only getting started, and the next discovery came from a very different direction. A separate team led by Ignace Uadzbalis at the University of Cambridge, working with Professor Roberto Maiolino, was studying a different early black hole using Webb, and found something almost the opposite of LID 568. This black hole sat about 800 million years after the Big Bang, making it one of the earliest ever detected, and it weighed roughly 400 million times the mass of the Sun. That made up close to 40% of the entire mass of its host galaxy, compared to a typical ratio of around 0.1% in black holes found nearby today. Despite being enormous, this black hole was barely feeding at all, pulling in gas at a rate around 100 times below its own theoretical maximum. Uadzbalis compared it to a bear gorging on salmon before hibernating for winter, a black hole that had already stuffed itself and was now lying dormant. Maiolino and his colleagues ran simulations suggesting that early black holes may cycle through short bursts of extreme overfeeding lasting 5 to 10 million years, followed by long naps lasting around 100 million years. Because those naps last so much longer than the feeding bursts, most early black holes would be caught resting rather than caught in the act, which helps explain why finding an active one like LID 568 felt so rare and so important. Two very different observations, one showing a black hole gorging at 40 times the speed limit, and another showing a black hole resting off a similar binge, were starting to paint a picture of a violent, uneven growth process in the early universe. But the most surprising twist in this whole story was still waiting to be uncovered, and it did not come from a new discovery at all. It came from someone going back and checking the old one. More than a year after the original LID 568 announcement, a different group of researchers decided to revisit the data using the Astrophysical Journal as their outlet for the new analysis. They wanted to double-check the extreme 40 times figure that had made headlines around the world. What they found flipped the story on its head. The team discovered that heavy dust surrounding LID 568 had thrown off the original calculations. Dust absorbs and scatters light in ways that can make an object look far more luminous or far dimmer than it actually is if that dust is not properly accounted for. Once the researchers corrected for the dust, LID 568 turned out to be feeding at a rate consistent with the normal Eddington limit after all, not 40 times beyond it. That does not mean the discovery was worthless. LID 568 is still one of the more actively feeding black holes ever found this early in cosmic history, and the powerful gas outflows Sue's team detected are still real and still worth studying. It is simply a reminder that even with a telescope as powerful as Webb, dust hiding around a distant object can trick even careful scientists into overestimating just how extreme something is. Follow-up studies are still planned to understand exactly how the dust around LID 568 is shaping what astronomers see. That kind of correction turned out to matter for more than just one black hole, because a much bigger mystery involving thousands of similar objects was unfolding across Webb's images at the very same time. Almost as soon as Webb started returning images of the early universe, astronomers noticed small, compact, unusually red points of light scattered across the data. They nicknamed them little red dots, and within a few years, hundreds of them had turned up. Nobody could agree on what they actually were. One idea was that they were incredibly dense clusters of young stars packed into a tiny space. The problem is that some of these objects appeared to be shining with the brightness of over 250 billion suns while measuring less than a third of a light year across, a size far smaller than the distance between our sun and its nearest neighboring star. Packing that many stars into that little space did not fit with anything astronomers understood about how galaxies form. The competing idea pointed to black holes, but that explanation came with its own headache. If a supermassive black hole sat at the center of each little red dot, it should also be blasting out X-rays, the way most known feeding black holes do. Telescope after telescope searched for those X-rays and mostly came up empty, leaving scientists with an object that looked like a black hole in some ways and did not behave like one in other ways. For a while, the little red dots seemed to shift shape depending on which instrument was pointed at them, and researchers openly admitted they were stuck. The breakthrough came from a team at the University of Copenhagen, led by Professor Daruk Watson, who took a fresh look at the highest quality spectra Webb had gathered from these objects. Instead of assuming the broad light signatures came from gas swirling and moving quickly around a black hole, the way astronomers normally interpret such signals, the team tested whether something called electron scattering could explain the pattern instead. That process happens when light bounces repeatedly off free-floating electrons packed into an extremely dense cloud of gas, spreading the light signature out in a way that can look deceptively similar to fast-moving gas. Once they applied that correction, the numbers changed dramatically. The black holes hiding inside little red dots turned out to be about 100 times less massive than earlier estimates had suggested, weighing somewhere between 100,000 and 10 million times the mass of the Sun, rather than the far larger figures first proposed. These are young, supermassive black holes, wrapped in a thick, dense cocoon of ionized gas, so packed with material that it explains both the missing X-rays, since the cocoon absorbs them before they can escape, and the strange red glow, since the light has to fight its way through that shroud before reaching Webb's detectors. The violent, messy picture finally made sense once the dust and gas hiding these black holes was properly accounted for. The same lesson that came out of the LID 568 correction, just applied on a much larger scale involving hundreds of objects at once. Put the pieces together and a pattern shows up across every one of these discoveries. A black hole appeared to be eating 40 times faster than physics allows, until a second look revealed dust had exaggerated the numbers. A separate black hole was caught napping after an apparent overfeeding binge, its enormous size hinting at violent growth spurts hidden in its past. Hundreds of mysterious red dots looked like impossible objects until researchers realized thick cocoons of gas were distorting what Webb saw all along. None of it was guesswork, and none of it happened by accident. Every one of these results came from careful work using Webb's IR spec and NIR cam instruments, cross-checked against Hubble and Chandra data, and published in journals including Nature Astronomy and Nature itself. A telescope built to study the first galaxies in the universe ended up rewriting the rules for how supermassive black holes are allowed to grow. Black holes near the dawn of time were supposed to follow the same speed limits as black holes today. Webb proved that the early universe was messier, faster, and far stranger than anyone had planned for. If this video gave you something, subscribing takes 3 seconds, and it helps us keep making content like this.